So this is a joint work with Huaxia Zheng, who's at the School of Economics at Shufei, Shanghai. In this paper, we investigate the possibility of designing attractive social choice rules in a setup where a planner has to choose one out of finitely many objects. These objects are of a public nature, and where agents have strict preferences over these objects. So the formulation is one where the planner knows exactly what she wants to choose for society for each profile of preferences. This is summarized by the social choice function. So these are the objectives of the planner. The only problem is that the planner cannot see the preferences of the agents. These are private information. So the design of the social choice function has to be such that it gives incentives for truthful elicitation of preferences. Now, this truthful elicitation of preferences can be modeled in many different ways. We opt for the strategy proof requirement, which has the merit that agents volunteer their true preferences independently of their beliefs about the realization of others' preferences or their strategic motives. So we investigate the possibility of, as I said, positive results in this setup. I will be more specific about our question presently after I've set out the model and given you some background material. So there is a finite set of voters, I. There is a finite set of alternatives, capital A. So A, B, and C are like, for example, the planner may decide to build a hospital or a park or a library, etc. So these are public alternatives. A preference ordering is a linear order over this finite set of alternatives. Rk of Pi will denote the kth ranked alternative in the linear order Pi. So of course, if k is 1, then we are talking about the top ranked alternative. If k is 2, we are talking about the second ranked, and so on. A typical preference domain will be denoted by script D. A generic profile of preferences is a P, which specifies a preference ordering for each of the n voters or agents. And we will use the standard notation of Pi, P not I, because we'll be talking about unilateral deviations in the context of strategy-proofness. And we will maintain the hypothesis that the domain is minimally rich in that for every alternative there exists at least one linear order which puts this alternative at the top. Another axiom that we will maintain here is one called unanimity, which says that if it so happens that we pick up a profile P where everybody has the same alternative, let's say B on top, then the social choice for that profile will be B. So society respects the unanimity of preferences across agents. This is a minimal hypothesis. And we will study social choice functions. So first, I introduce what a deterministic social choice function is simply a map from profiles to alternatives. Now, if we require this social choice function f to satisfy strategy-proofness and unanimity, then the celebrated Gibbard-Satterthwaite theorem tells us that the only social choice functions which satisfy these criteria are the dictatorships. And this is a fundamental negative result which has shaped the subsequent development of this literature. What the literature has done thereafter, primarily, is to argue that, look, in specific economic contexts, political economy context, for instance, there is some structure on preferences so that not all preferences are allowed. So Gibbard-Satterthwaite says that if D is set to be the universal domain, all strict preferences, then you get dictatorship. And the literature has thereafter looked at what are called restricted domains of preferences, where not all preferences are admissible, and has tried to argue that we can have nice possibility results. That means we can discover nice social choice functions which are strategy proof and which allow for an equitable distribution of power in society. A case in point is the celebrated single peaked domain, where indeed has found very large applications in public economics, in political economy, etc., where there's a class of rules called these median voter rules, which are non-dictatorial and strategy proof. But this literature broadly is called the restricted domain approach. But a word of caution is in order here. Just by looking at restricted domains, one cannot be assured to move away from dictatorship. Indeed, there are instances in the literature of restricted domains where the conclusion of the Gibbard-Satterthwaite theorem nonetheless holds. So these are actually much smaller domains where the negative dictatorship conclusion remains valid. So this shows that the Gibbard-Satterthwaite negative result is in fact quite robust. And furthermore, that in general, the study of restricted domains is quite nuanced. How you restrict the domain matters a lot. So a natural question that has sort of been there lurking in this literature for a long time now is, what is the sort of converse of the Gibbard-Satterthwaite theorem? And that is what we are trying to address in a very specific context in this paper. So the question we are asking is, supposing we know that a particular domain allows us to construct some nice strategy-proof rules, what can we infer about the structure of the domain? So this paper is about characterizing domains rather than characterizing rules. So I will be more specific about the setup and the results. But before I do that, I would like to generalize the analysis to random social choice functions. So we are going to give the planner some additional flexibility in that she can choose lotteries over outcomes rather than just deterministic outcomes. So I will do that first. Then I will argue that there is something to be gained, something meaningful to be gained by allowing for randomization. And then I will proceed to answer the question that I posed here, which is trying to characterize a domain which allows us to design nice rules. A random social choice function is a map phi from profiles of preferences to lotteries over A. Once again, we will focus attention on unanimous random social choice functions, which say the obvious, which is that if I happen to pick up a profile where everybody is unanimous that A is the best ranked alternative, then the social lottery puts probability 1 on A. So my notation here is phi of A is the weight that the social lottery puts on the alternative A, and that is 1 by unanimity. The notion of strategy-proofness here was actually introduced by Gibbard. It's an ordinal notion of strategy-proofness, which says that the lottery by truth-telling first order stochastically dominates the lottery by lying. So on the left-hand side, this is the lottery that the agent I gets when she reports her true preference Pi, and this is the lottery that she gets when she reports the manipulation Pi prime. When t is equal to 1, this inequality just says that the top-ranked alternative of Mr. I under her true preference gets at least as much probability as it gets under the manipulation. When t is equal to 2, it says the sum of the first two get at least as much probability, and so on. So that's just first-order stochastic dominance. So this is an ordinal version of strategy-proofness, which was introduced by Gibbard, and we're going to follow that here. And this has the feature that if you compute the expected utility of this agent under truth-telling, that's going to be higher than the expected utility of a manipulation for every possible Bernoulli utility that represents this person's preference. So it's a very robust form of strategy-proofness. So we will stick with this. Now that we've allowed for random social choice functions, the question is, what does it give us additionally? Well, one possibility immediately reveals itself. Supposing there are just two people in society, agents 1 and 2. One way of constructing the social lottery would be to assign a fixed probability to agent 1, let's say half, and the remaining probability to agent 2, half, with the understanding that whenever they announce a profile, I will pick agent 1's peak with probability half and agent 2's peak with probability half. Now these probabilities are held fixed. They are not they cannot change with the agent's announcements. So obviously this is going to be strategy proof. I don't mean obviously strategy proof, I just mean strategy proof, and the argument is simple. By manipulating your preference, the only thing you can do is divert the probability half that has been allocated to you to a worse ranked alternative. Now that's not a very clever thing to do. So a random dictatorship is indeed strategy proof, and it's strategy proof on any domain of preferences. So this is something new which goes beyond the usual dictatorships, right? And why is it different? But it allows for an equitable spread of power in society. So this seems like an improvement over dictatorships. So these things come into play once you look at random social choice functions. The question is, are these completely satisfactory from the point of view of design? And I will try and argue that no. And I do so by an example. For example, again with my two agent setup, suppose the peak of agent 1 is A, the peak of agent 2 is B. Suppose agent 1's worst alternative is B and agent 2's worst alternative is A. And furthermore, it's a hypothetical case, suppose that they share a common second ranked alternative, C. In such a setup, one may argue that it makes sense to be able to give some positive probability to the alternative C. It's a compromise alternative here. But random dictatorships forbid us from doing that. The only alternatives that can get positive probability are those that show up as somebody's peak. So this lack of flexibility of random dictatorships is what we criticize. And we say that it's an unsatisfactory scheme. So the question is, are there other random social choice functions which are not random dictatorships, but which are nonetheless strategy proof? And here there is a celebrated theorem of Gibbard in 1977, where he proves that, again, on the universal domain of preferences, the only strategy proof unanimous social choice functions are random dictatorships. So this is another actually strong negative result. Why is it negative? I argue that adding randomization only generates the obvious new things, which are convex combinations of deterministic dictatorships. You get nothing new, nothing beyond that. So this is actually a very strong negative result. So let me just quickly summarize the discussion thus far. I'll draw a diagram first. So if this is my universal domain of preferences, script U, then I've mentioned to you that in fact there are restricted domains much smaller than U, where the Gibbard-Satterthwaite conclusion still holds. And these are called dictatorial domains for the obvious reason that strategy-proofness and unanimity precipitate dictatorship even on these domains. That was the first thing I mentioned. And then I just write down Gibbard's theorem, which actually implies the following relation. On the universal domain. So on the universal domain, Gibbard's results imply a very strong negative relation, which is that deterministic dictatorship precipitates random dictatorship. You get nothing really new. So one conjecture is whether this kind of relation is going to hold on an arbitrary dictatorial domain, which could be smaller than the universal domain. So given an arbitrary dictatorial domain, is it going to be the case that it must necessarily be a random dictatorship domain? So that seems to be a reasonable conjecture to make in this context. And the answer is actually, fortunately, this conjecture is false. So there is a breakdown in this relation between dictatorship implying random dictatorship when you look at restricted domains. And an example of this failure is illustrated in this diagram here. So this is work with Arunava Sen and Hwasha. We actually constructed a counterexample. So this is an example with 5 alternatives. I've arranged them in a graph, so I'm yet to explain to you what the edges mean. I'll get to that later. But this is an example of a domain with just 5 alternatives where you can construct a rule, a random social choice function, which differs from random dictatorship. Why? Because we are able to give positive probability to some compromise alternatives. Now, recall these compromise alternatives were things that are sort of second rank for both agents. So we were able to construct certain profiles where you can give positive probability to these compromise alternatives. That itself ensures that this is different from a random dictatorship. And we verified the strategy-proofness of this. So this is like a counterexample to that conjecture. Now, this domain that we work with is in fact for a dictatorial domain. So if you were to restrict attention to deterministic social choice functions, this domain is actually dictatorial. Now, what do these edges mean? Let me just very quickly illustrate. So there is an edge joining A4 and A1. What that means is that I can find two preference orderings, one which has A1 on top and A4 second. I don't care about how the others are ranked. And another where these two are flipped. So A4 becomes top, A1 second, and again, I don't care about the others. So whenever I can find two preferences with this structure, I have an edge on the graph. So given this many edges is enough to get dictatorship. So of course, the universal domain will have all kinds of edges and everything else, but we don't need so much. So this domain is actually a dictatorial domain for deterministic social choice. So this is the reason why I'm trying to argue that randomization adds new possibilities when you look at restricted domains. Because these, the random social choice that I talked about here, these cannot be expressed as convex combinations of deterministic dictatorships. You're getting something new. So this is the starting point of the question we ask here. The question we ask in this paper is, supposing I know that I'm in a setup, in a restricted domain setup, where it is possible for me to design a random social choice function which is flexible. Flexible means it departures from random dictatorship in this minimal sense that I said, which is that whenever there is a reasonable, natural compromise alternative, the random social choice function must give it strictly positive probability. That is my point of departure from random dictatorships. And I ask, if a domain allows me to do that, what must it look like? So that's the sort of converse question that I sort of alluded to at the beginning of my talk. So that's what we're going to be doing in this paper. And we're going to specialize the setup to a very particular context, which is the following. We assume that we are in a multidimensional world. So the set of alternatives is a Cartesian product of m components. Each component has at least two alternatives. So here, the kind of applications one thinks of is when a planner is trying to choose on two dimensions, expenditure on education and expenditure on health. So these could be two components, and there are different alternatives. So that's the setup we are operating in. And I also impose some preference restriction. And this preference restriction is called top separability. What does it mean? Supposing I'm comparing two alternatives which are similar. What do I mean by similar? They disagree exactly on the component S, and they agree everywhere else. Right? So it's only on education that these two alternatives differ. The first alternative, let's say, specifies a higher amount for education, the second one a lower amount. When this happens, and suppose A is inherited from the peak, then this alternative must be ranked higher than this one. This is called top separability. We will henceforth restrict attention to top separable preferences. And I just say that a multidimensional domain is one where all preferences are top separable. I would like to emphasize that this domain assumption is not innocuous. This assumption of top separability allows us to look at new kinds of rules. For example, I'll give a simple example. Again, going back to the two-agent world, it is possible for me to anoint agent 1 as the dictator for education and agent 2 as the dictator for health. Let them choose their favorite points, and we sort of piece it together. That becomes strategy proof here. So there are new possibilities tied to the multidimensionality which become possible here. But these are not the rules I'm interested in. Why? Because these do not systematically select compromise alternatives with positive probability. So within the class of top multidimensional domains, I will narrow down the search now for domains that systematically allow us to talk of compromise. Couple of examples of domains that satisfy top separability. The first is fully separable preferences, which say that I can talk about marginal preferences on each component coherently. So there are marginal preferences in each component, and those can be used to construct the social choice. So that's full separability. This was introduced, or studied in the very least, by Le Breton and Sen. It was introduced much earlier. I recall a paper by Barbera, Sonnenschein, and Zhu, which did that for two alternatives. Another commonly studied preference restriction in the multidimensional world is a generalization of the idea of single peakedness to multiple dimensions. So please recall that usual single peakedness says that the alternatives are arranged on a line. Let's say A7, A5, A1, A2, and so on, blah, blah, blah. And supposing the peak of an agent happens to be A2, then on each side we have a decreasing relation of this type, which says that as you move closer to the peak from either direction, your preferences are improving. But it imposes no comparability on opposite sides of the peak, which is why I use different colors, pens for this. So this is the usual single peakedness on a line. So Barbera, Gull, and Stacchetti generalize this to a product of lines, so multidimensional context. And what we do in our paper is generalize it further to a product of trees. So let's again assume that there are two components, education and health. And on education, the alternatives are arranged in a tree. Likewise for, what was this one? Education, health. So this is a trivial tree. And then you construct the Cartesian product of these two trees. That gives us this object here. And now we can talk of single peakedness in this context, again borrowing the same idea that I used here. So for instance, if the peak of a voter happens to be D11, let's say that's the peak that corresponds to A2, and consider the alternative C10. Now, if you want to move from C10 to the peak along this tree, there are two routes. One is via this C11 and the other one is via D10. So these two alternatives are, in a sense, between the alternative C10 and the peak. So they should be ranked higher than C10. That's the natural generalization of single peakedness to a product of trees. So this is another instance of a preference satisfying top separability. Now, at this point, I would just like to note that in case I were to argue that a domain is multidimensional single peaked, then it is incumbent upon me to derive a tree on each component and then show that preferences are going to be single peaked in this sense on the product of the trees. That's the amount of work that one has to do if one tries to argue that a domain possesses a multidimensional single peaked structure. Okay, with that caveat, let's go on. Now, I'm going to introduce my point of departure from random dictatorships. The idea was that I need to institute a systematic way of giving positive probability to compromise alternatives, and I will use this property to generate some structure on the preference domain. So this is the input I'm putting into my analysis. So I would like this to be as weak as possible, systematic but weak. So this is a compromise property which says that supposing I have a profile of preferences P, where approximately half the people have the same peak, which is XS A minus S, and the remaining half, which need not be exactly half, it could be approximately half, have a different peak, which is similar to this one. So it differs only on the Sth component. All right. Supposing I have a profile P, where half the people have something on top, which happens to be this alternative, and the other half has this on top, and furthermore, they have a common second, which also looks similar to these, except that it has a Z here. In such a special profile, I will insist that the random social choice function gives this compromise alternative strictly positive probability. So my notion of a compromise is very, very sort of, how to put it, delicate. It's only in very, very special situations that I'm, singling out a compromise and insisting that it gets positive probability. Of course, the social choice function can be much more flexible and give positive probability to many more things. Of course, I'm absolutely fine with that. But this is the minimal I require. And in some sense, I'm trying to keep it as trim as possible so that my result becomes stronger. So this is the notion of compromised, the constrained compromise property. It's a weakening of an earlier condition that we used in an earlier paper. This earlier paper examined domains which are excluded from multidimensional domains which are excluded in this paper. So we are studying something which was not covered by this paper, and we are introducing a weaker version of this compromise property. And finally, I can be more precise about my question. Suppose a multidimensional domain allows us to design a unanimous strategy-proof random social choice function which respects this constrained compromise property. What can we infer about the structure of such a domain? Now, in order to implement such an exercise, we need enough preferences in the domain for strategy-proofness to have bite. If there are very few preferences in the domain, then the opportunities for manipulation are minimal. Strategy-proofness has very little bite. So we need some kind of a richness condition. This is very standard in this literature. So you need enough preferences so that strategy-proofness becomes a non-trivial restriction. So how to model enough? So that's the next part of the talk. I'm going to introduce a notion of richness on the preference domain, which will allow us to give a precise result. So one notion of richness that has been proposed in this literature and has been used quite extensively recently. Recent papers are ones by Shin Sato in 2013 and Wonki Cho 2016, but there are many others as well. It can be traced back to earlier work by Monjardeh and Grammont. So the idea is the following. You start with two preferences in the domain, pi and pi prime, which appear very different. But the domain is such that it allows us to move from pi to pi prime using a sequence of preferences, each of which is very close to its predecessor. So as you move from pi1 to pi2, exactly one pair flips. Everything else remains the same. Then from pi2 to pi3, the pair db flips. Everything else remains the same, and so on. So these preferences, pi1, pi2, and then pi2, pi3, are called adjacent preferences because they differ exactly in one flip. And the domain is connected when I can connect, I can find a sequence starting at pi, culminating at pi prime, where all sort of contiguous preferences are adjacent. So basically the idea is I can reconcile the differences between pi and pi prime by a sequence of small flips. So this is the notion of adjacency. This has been used, this notion of richness has been quite useful in this current literature on this topic. So the natural thing to do would be to try to use this notion of richness in our study as well. Unfortunately, it fails in our context. So since we are in a multidimensional setup, we have to be prepared for separable preferences. So let's look at the same exercise, but in a context of separable preferences. So there are only two components, 1 and 2, and on each component there are only two alternatives, 0 and 1. So there are 4 alternatives in my story. So here I start with the preference pi, and here I end with the preference pi prime, again different. And I'm trying to implement the idea that I can move from pi to pi prime by a sequence of 1 flips. Unfortunately, I cannot do that anymore because the moment I flip A and C, I'm upsetting the marginal preferences on component 1. And that perforce requires me to flip D and B as well. So because of separability restrictions, it's impossible to actually implement adjacent flips. So we have to be prepared to flip actually more than one pair of alternatives in general. And if we are prepared to do that, then we can actually construct a sequence starting here and ending there, etc. So here these are called pi and pi prime are called adjacent plus preferences because we are going to flip all the things that are sort of required by a separability argument. So these are the sort of sequences of preferences that we will postulate. And so we will require these adjacent plus preferences to be separable, and the flipping alternatives are going to be exactly those ones that are required by separability. So this is going to be the language we use to talk about rich domains. So we talk about paths, as I said earlier, and our notion of a path is more general than that of this earlier literature. But now we need some more structure on these paths. We don't want these paths to be, completely arbitrary and wander all over the domain, because that becomes very difficult to work with. So we want some structure, some parsimony in the description of these paths. So that's what I'm going to do next. And once I've done that, the resulting domain will be called a connected plus domain. So now the last piece of sort of notation and technical definition I'm going to show you is the formal definition of a connected plus domain. So please bear with me. The connected plus requirement has two kinds of restrictions. The first restriction is called the interior plus property. What this means is, supposing I take two preferences which have the same peak, I should be able to find a path, an adjacency plus path, which starts at the first preference, ends up at the last one, such that all along the path, all the preferences have the same peak, the same common peak. So you remain in that subdomain. So that's called the interior property. You remain in the interior of that subdomain. This makes life much easier. As you can imagine, these things can get very, very cumbersome very quickly. So this is an important thing. And then we have another property called the exterior property. This time we are looking at preferences which have different peaks. So in some sense, they lie in different subdomains. So you're going to transit from one subdomain to another. That's why it's called the exterior property. And this says that whenever you have two different peaks, and supposing given two alternatives which share the same ranking across these two, I can find a path connecting them which respects this ranking of A and B all along. This is called the exterior property. Furthermore, when the two peaks are similar, recall similar means that they disagree on exactly one component, then the entire path also has the same structure. So this is called the non-detour property. Again, without these, it's possible to state results, but it gets very, very cumbersome. So we use these two definitions. So a connected plus domain is a multidimensional domain satisfying the interior plus exterior property. All the examples that I alluded to before fit sort of are included in this definition. The entire top separable domain, this fully separable domain, the multidimensional single-peaked, their sort of hybrid domains, which are intersections and unions, etc., can also be reconciled within this framework. There are some domains which are, of course, excluded as well. The complete domain is excluded because we are looking at top separable preferences. Then, the one-dimensional models are excluded from the story. So finally, I'm in a position to state our first result. That's the theorem. Theorem has two parts. The first part is the main result. Supposing D is a minimally rich and connected plus domain, if it allows us to define a random social choice function which respects unanimity, strategy-proofness, and the constrained compromise property, then it must be multidimensional single-peaked. So this is our principal finding, because we are trying to extract the structure of a domain which allows us to construct a nice random social choice function. Again, as I had mentioned earlier, this requires us to extract from our hypotheses a tree on every component, and then take the Cartesian product of those trees, and then finally argue that the preferences must be multidimensional single-peaked on the product of these trees. So this is the sort of result, the sort of converse result that we were talking about. There is also a sort of a counterpart to this necessity argument, which says that give me an arbitrary multidimensional single-peak domain, I can always define a random social choice function which respects the three properties. Now, this part of the theorem is not terribly exciting. As you can imagine, we can replicate the one-dimensional ideas look for a median voter on every component, piece it all together, and randomize over all these median voters, and you get a nice social choice function that allows us to give positive probability to compromises. So this part of the theorem is basically for completeness. A little bit of work has to be done to make it happen, but it's not the most exciting thing. The really important thing from my perspective is the first part of the theorem, where we reverse engineer the attributes of the domain from the existence of a well-behaved, nice social choice function. There is another theorem where we restrict attention to deterministic social choice functions, and there it does not make sense to impose the compromise property, because deterministic means I can only give probability 1 to one alternative. So here we replace the compromise property by the standard usual requirement of anonymity. Anonymity is the polar opposite of dictatorship in that no individual has any power in society. So this is our way of modeling departure from dictatorship, of modeling equitable social choice functions. So we study that, minimally rich and connected plus domains as before. If it allows us to construct a unanimous strategy proof rule that satisfies anonymity, then it must be multidimensional single peaked. The previous result had a precursor. This was earlier work with Arunava and Zheng, where we looked at domains which excluded multidimensional domains. Furthermore, we had another axiom on the social choice function called the tops only property, which plays a fundamental role in much of this literature. The tops only property says that the social lottery is determined by the peaks of the voters' preferences. It does not say that only the peaks get positive probability. Anything can get positive probability, but the social lottery is completely determined by the peaks. This was an axiom in our earlier work, but in the present paper, we are actually able to endogenize this requirement. Strategy-proofness and unanimity, it's a first step of the proof, guarantees the tops only property. So that's another improvement over this earlier literature. And the same is true for this theorem vis-a-vis earlier results, earlier these two papers. So a quick mention of what earlier work here has been. This idea of working towards converses, this idea has been there in the literature for a while. An early attempt to do something similar was by Bogomolea in 1998 in a PhD thesis. She tried to show that conditions under which a strategy-proof rule, anonymous strategy-proof rule, could be understood as a median voter rule. But there were no domain implications in her study. More recently, Nering and Puppe, in a series of papers, I've quoted one of them, have a very general notion of generalized single peakedness, which they show is sort of implied by strategy-proofness and other applications. But it's a very general algebraic structure. So it includes the complete domain, for instance. So it's not a very structured result along the lines that I've been talking about. More recent work I have done with Arunava and Remzi Sanver was along these lines. We in these two papers, we obtain versions of single peakedness with some additional hypotheses, which is the tops only property is imposed artificially. And there is another restriction on the number of voters. We can only handle even number of voters in our necessity theorem. This paper, this result, actually improves on this one in the sense, it improves, and I wouldn't say improve, it gets a sharper result. It gets full multidimensional single peakedness without tops onlyness, but by making a much stronger richness assumption. Our richness assumption, connected plus, is very, very carefully elaborated, calibrated to the multidimensional structure, and that gives us the wherewithal to actually prove a stronger result, where the tops only property is endogenized, and we recover full single peakedness from our analysis. So this is a sort of summary of what the paper does. There are many counterexamples trying to show that these axioms are needed for a theorem, etc. I will not get into those things. I'll stop 5 minutes early, so if there are any questions, I'll be very happy to answer them. So
that you said that the endogenous top-only property, but that together with this richness assumption.
yeah.
So unanimity and those things, strategy-proofness.
Yes.
The richness assumption.
Absolutely right. The richness plays a fundamental role in this. Yeah.
So without then probably strategy-proofness doesn't really
No.
much.
No. Without the richness, it's hard to proceed. So there is a way of course, if you like, I could weaken the richness condition a little bit and put in topsoliness as a separate axiom, but it doesn't buy us too much actually, because recovering these trees, as you can imagine, is a bit of a pain. So we need the strong richness condition, a connected plus. But in my defense, I will say that most domains that you're interested in the multidimensional context satisfy the richness condition. So that's the thing.
Probably it's going against what you wanted to do, but so in terms of social juice function, so that you get any other property other than boundaries that could be so you are imposing those assumptions. So that has some structure implications of
The only assumptions I'm putting in are unanimity, anonymity, and strategy-proofness.
and that implies top.
That implies tops only.
Do you think anything else could be implied from?
Efficiency can be implied in unidimensional models, but not here. On a multidimensional model, you don't get efficiency. So what else could we get? I guess, I don't know. I really haven't thought about it too much, but neutrality could be imposed, but we don't need it for this mechanics here. So. Okay, thank you very much for listening. Thank you to the organizers for this opportunity. Thank you.